Okay, for our speakers, there's a change in plans. We're going to be driving the presentations from the back, not from here. So, Julie, because you have a lot of notes, I will try to drive yours from here. But the other ones are going to be driven from the back because we cannot get this to sync unless we want to do a lot of slide projector research, which is not why we came here. Can we get the doors closed in back, please? So I want to give a little bit of an intro to what we do here in the R&E track at NANOG. For those who are new, a lot of people who are here who work in the research and education community, both in the public and private sector. And what I mean by that is there are plenty of research organizations that exist out there that do network research that are actually for-profit or even non-profit 501c3 corporations that would not fall under what we normally think of as public sector research and education. Everyone is welcome to the track, so we like to have as many people, as many diverse opinions, as many viewpoints as we can get here. Thank you all for coming. Where did this really come from? There are sort of two threads that built the research and education track. The first was the research forum. The research forum is still part of NANOG. You can submit a talk and you can ask that it be part of the research forum, and it will either go into this track or it will go into a very similar track. What the research forum is for the types of network research that are kind of not quite yet at the point where we're willing to say that this is completely baked. And I don't mean that in a bad way. I mean that in where we're really thinking about what are the avenues for further research, what are the things that we want to think about when we do the kinds of network research that we're doing. And a good example of that is really kind of asking the question, what question should we be asking? And that's something that's not that easy. And one of the issues that researchers often have is, I can't actually know whether I'm asking the right question because I don't have enough input from operators. I don't have enough input from the people who are actually doing things out there. And the result is that we end up with research or with projects that happen that do things like try to turn the entire DNS into a distributed hash table. I think a lot of us remember that about 10 years ago. We were all seeing all these presentations about how DNS would all get fixed because it would all become a great big distributed hash table. And distributed hash tables are very interesting from a theoretical perspective, but from an operational perspective, all of the problems they posited to solve were already being solved within the existing DNS protocol. And there's some of that also with BGP. There's some problems that need to be solved in BGP, and there's some problems that don't really need to be solved yet in BGP. There's a lot of concern about excessive BGP churn and excessive bloat of the routing table. But as Jeff Houston, who's sitting right in the middle back there, has said, actually that's not that big of a problem. As the BGP routing table has scaled, so has the quality and so has the capabilities of routers, but also the protocol is scaling along with the table. So a lot of questions that are being asked and a lot of research problem statements we kind of need to make sure that they are aligned with the operational concerns that we have, and that's part of what we're trying to do, and that's part of what the research forum tried to do. The other thing that the research track tries to do is bring in the kinds of operational talks, and we're going to see some of those today as well, that would have been at the Internet 2 Joint Techs or the Net Gurus meetings. Those are meetings that happened under the auspices generally of the Internet 2 community. Internet 2 Joint Techs has become the Internet 2 Tech Exchange, but it only happens once a year. It's very large, it has many tracks, and it's kind of a little bit more of a zoo, shall we say, than the kinds of technical meetings that we all like to get our hands dirty with. So this is an attempt to kind of bring back some of that aspect of it. So while we're on the subject, what kinds of other meetings are going to be happening in the R&E community? The Quilt will be having their member meeting. The Quilt is a group of research and education networks in the US that basically it's just a loosely affiliated organization. They'll be meeting in Austin. That is at the end of September into the beginning of October. And then you'll notice something really strange about the Tech Exchange along with NANOG. And I'll mention that in a minute, but I'm also not sure what's happening with the NetGuru meetings because Jeff Handel, who was running NetGurus, has left LSU, and so he's doing something else now. And I don't know who's running NetGurus. So if anyone knows what's going on, let me know. But yeah, you'll notice something interesting about Internet 2, Tech Exchange, and NANOG there at the same time. So some of you may want to go to Cleveland for Internet 2 Tech Exchange. I can tell you I'll be going to Montreal for NANOG in October instead of Cleveland. Just saying. What are we going to do today? A couple things. We're going to end a little bit early because I do want to give people time to go to the very first ever dedicated Peering Personals block, which is going to happen at 5 o'clock. There's no space in between us and them. So we are supposed to end at 5 o'clock, or you're supposed to end at 5 o'clock, and they're supposed to start right then. To give us time to get upstairs to the California room, I'll end about 10 minutes early. I'll try to end about 10 minutes early. So we have a bunch of content. We may not get to all of it. I'm always willing to be the Matt Damon who gets bumped at the end. So let's just get started with it. The first talk we're going to do today is going to be Murat Yüksel. I hope I got your name right, Murat. He's a professor at University of Nevada, Reno. Is that right? I remember that. Yeah. He's going to be talking about training network administrators in a game-like environment. I really kind of like these sorts of things. Part of the reason I'm interested in using game environments as a way of bringing sort of solving problems is that the building I'm moving into, we are arranging our seating and we're doing it in a game environment, how we actually sit and whether we sit in cubicles or in offices or things like that. So Greg, back there, why don't you bring up Murat's talk, and Murat, why don't you come on up? This is going to make you go forward. That makes you go back. If you push that, it'll blank, and the guide is right here. So you don't have to look at that. Okay.
All right, thank you. So, glad to be here. I'd like to probably say that I have another hat. I'm on sabbatical right now and working at a startup company which does performance improvement for Hadoop clusters. It's called Pepper Data, the name of the company. And I would love to talk more about the big data issues offline. I'd like to acknowledge my collaborators, Dr. Gunesh and Dr. Humanfar from CSE and psychology departments of UNR. And most of this work was done by my graduate student, Engin Arslan, whom I'm working with in the same startup company, as a matter of fact, just as a note. And of course, this was funded by NSF. We are so grateful for that. As I guess it's probably needless to say, that network management and automated configuration of really large number of parameters is a big problem. You have got SLAs to meet in an ISP environment, and you have got high demand applications. Again, putting restraint on how you handle your network itself. A lot of the times, in an ISP environment, you end up getting in a failure, demand spikes, and responding to them in a timely and smart manner is, of course, a critical issue and means real dollars. According to the people that I've talked to in ISP community, a lot of the times these complex management problems, complex management and configuration problems, are a lot of the time solved by human admins. They're just too complex to trust on an automated script. And again, since the amount of stake is too high, you just don't want to trust on a particular script that might just do something wrong in terms of a response. Again, according to the people in the ISP community whom I'm talked to, learning how to admin a network in the best manner is a long-term process, involves apprenticeship. You spend maybe years on a particular network, sort of you become the guru of that network, and sort of come up with, develop sort of like reflexes almost. If something goes wrong in this spot in my network, here's what I'm going to do, or if something comes up in this part of my network, here's what I'm going to do. So this is what I was told. And we thought that this is a good problem to attack academically as well, because it involves really interesting stuff coming together and really an interdisciplinary agenda. So the question we asked was, can we train the network admins by using tools that might involve simulations, or maybe even more than that, more interactive simulations like games, to reduce this amount of time that is needed for training the admins. Sort of like the flight simulator. You have essentially a pilot going through the flight simulator training for many days, many weeks, before really you are trust a billion-dollar plane to him. So it's very similar concept. You don't want to put a network admin who may just do some wrong responses and cost hundreds of thousands of dollars in terms of customer revenue. Then the question was, okay, well, how can we prove this hypothesis? So what is a particular network management problem that we can attack and show the concept in a small, quick and dirty prototype? I have to admit, IGP link weight setting problem is something that I worked on in other contexts, so this was more appealing to me. And apparently it needed to be something that is NP hard, and this is a known NP hard problem. The problem is essentially to set your IGP link weights, tune them in such a way that you load balance the traffic in your network. And of course, the problem is very difficult. It involves things like if you set the configuration wrong, you may end up getting into instabilities. If you trust the setting of the link weights to automated scripts, like for example, one intuitive idea would be, well, if the link has more congestion, you just automatically set the link weight based on that congestion amount. Well, it is known that that kind of automated response to this problem causes instability, actually route flaps. So we took this problem. As a matter of fact, I also verified with an ISP colleague that there are typically teams who actually work on this problem within a network operator setting on a 24/7 basis. I'm going to skip this one. So this is just illustrating one thing that happens, right? So you've got two flows, right? Because of the shortest path routing, they collide in a particular link. So over time, that link gets congested. So what you would do, you would just increase the link weight of that link from 5 to 20, let's say. And then the hope is that this is going to happen, right? So you're going to have the blue flow is, following another path. So this is what we called is decoupling flows, right? So you would like to decouple flows so that they actually follow different paths. This is a skill that you would need to develop over time in order to respond to this problem in an appropriate way. So the next question was, what is, again, a quick and dirty thing that we can do to experiment with this idea of using a game kind of environment to train network admins? About 4 years ago, NS3 was still in its infancy, so we had NS2. So we used NS2 simulation engine and wrapped it with a GUI. And the way essentially they interact is, essentially what we need to do is we need to provide a GUI to the player that gives him the impression that there's a real network running in the back. And in the meantime, in the back end, we would like to be able to simulate things like failures or link recoveries and so on, and observe how exactly he or she will respond to those dynamic events and measure things in the back end. So the way that they will interact is essentially we are going to give a particular network configuration, network scenario to the simulation engine, and simulation traces are going to be fed to the GUI. of course, and that GUI is going to display the network situation. It's going to essentially animate that to the player, and the player is going to give a response to it. And for example, in this particular case, it will be changing the link weight. And then the link weight is going to get changed in the engine, and then engine is going to calculate new shortest paths, and then new set of simulation traces are going to be sent back. So this is essentially a typical animation kind of thing. But of course, there's the interactivity that we have to have in order to prototype the concept. So NS2 doesn't really have all of that, so we had to add that kind of real-time interactivity. I can talk more about the details of how exactly we did this. We have more details in the papers. But essentially, the concurrent running of these two processes was really challenging, and giving the right feeling. I mean, you don't want to slow down the engine extremely because you're not going to be able to simulate anything. I mean, you don't want to do a pure real-time simulation. On the other side, you don't want to let the simulation engine run completely independently, because you want to make sure that it's slowed down a little bit, and so that it can get feedback. It can get the changes from the GUI. So we just used some TCP socketing tricks between the engine and the GUI to essentially do that. Just to give you an example, a link weight change means that, for example, the GUI sends a command of this kind, where between node 1 and node 2, the link is now going to be changed. The link weight is going to be changed to 2. And likewise, the simulation traces for every single packet, not every single packet, an aggregate set of metrics that relate to the traffic are actually sent to the GUI so that they can be animated for the player. This is just a snapshot of what we call as network management game. Clearly, this is showing, well, let me go through the interface just a bit. This is a very simplistic topology. One challenge, of course, is to come up with good visualization tools. If you were to extend this concept to really large-scale networks, how would you do it? In terms of just the visualization of the network itself is a big issue. Very nice research issue, I would say. For this particular routing problem, we gave the player the knob for every single link of incrementing or decrementing the link weight. If the player presses the green button on the link, then it will increment the link weight, and for the red button, it's going to decrement the link weight. And in this particular scenario, as you can see, there's a failure between Chicago and Atlanta nodes, and that, there it is reflected with a dark color. And every single link has some color showing the load on that link in terms of the traffic. And the goal of the game is to maximize the total throughput amount, which is on the right top of the interface. And there are several other things being shown, lost packets, the total transmitted packets from the beginning of the simulation and so on. And this is yet another case showing congestion between Seattle and Kansas with red colors of the links. So again, the way that the game progresses is that the player is going to see these things in dynamic manner and then respond by changing the link weights. Again, the goal is to increase overall throughput. It's possible that one can come up with other goals. We found this to be the best, particularly in this particular problem that we are attacking, the IGP link weight setting. Even in a simple network, actually, things may not be so easy. If the link weights are showing A, B, E path, right, the total throughput you can get is 1 megabits per second, but you may be able to find a better path, higher bandwidth path, by changing the link weights. So we exposed this particular problem to the players as well and observed how they played with it. We have conducted a bunch of experiments with the forced voluntary participants from the lab. So we essentially had two sets of experiments. Consulting with the psychology collaborators, we designed the experiments in two ways. One is we let the players progress to the next stage, which means just another network scenario we give them, without mastery. We just give them a particular amount of time. They spend 5 minutes, 3 minutes on a particular network, maximizing the throughput, and then move on to the next one. The second one is training with mastery. In this particular one, we targeted 2 particular skills and wanted to make sure that the player achieves the solution for that particular case before moving on to the next one. This is showing, I'm not sure if this green line is showing up nicely, but there's a green line if you look at it carefully. This is showing the life of an experiment, how exactly it shows. The vertical axis is showing the normalized throughput, normalized to the maximum possible throughput for that particular network. And we are essentially exposing some failures. Links are failing in the network. And just to come up with a comparative basis, the blue line is the case when there's no player. Essentially, you just let the network run. If nobody responds to these failures, essentially throughput goes down. And if you can look at it carefully, there's a line that goes up in there with a green. So right after each failure, you can see sometimes decreases in the throughput. And then player essentially responds to those by changing the link weights and then improves the throughput back up again. So that's how exactly it looked. Training, let me quickly go through the training without mastery results. We had 5 training scenarios. For every scenario, we gave the player about 3 to 5 minutes. And we had 8, we were able to convince 8 of the lab members to take this experiment. And each experiment, in total, took about 45 minutes, and we had both failure and no failure cases. This is showing the experiment design. So we first gave every single player a tutorial about the whole thing, what exactly we are doing, how exactly it works, and made sure that we are not really sampling anything that is transient. And then before we start the training, we gave 2 cases. One is number 6 and the other one is number 7. And number 6 had no failures, number 7 had failures in them. And then we essentially exposed 5 training scenarios with increasing difficulty. Difficulty being like the number of nodes, number of links in the network, and the number of failures if there are any. And then after that, we changed the number 6 and number 7 just a bit. Not a lot. I mean, think about, like, for example, Internet 2 network, about a dozen or so backbone nodes. You just maybe change 1 or 2 links in there, change the link weights, initial link weights, so that we can observe a similar thing. Honestly, coming up with a before and after training experiment is an art. It's not so easy. Looking at the best and the worst players. So this is showing, on the left-hand side, we have got the worst player for this. On the right-hand side, we have got the best player. And the blue line is showing the cumulative throughput that particular player has achieved on that particular experiment. And this is case number 7, where there were failures. And as you can see, the worst player is, the best player actually still improves actually significantly. After the training, this is what you see. After the training, you actually get some changes, but worst player is still actually not doing well. This is actually showing side by side. This is the best player performance on the left-hand side before training, on the right-hand side after training. So the best player did learn actually quite a bit, as you can see. The worst player probably did not learn much. So you can, for some people, you can't do much. This is the summary of actually those experiments without player. Before training, those actually, as you can see, there are 8 bars. Each of them is the final throughput amount, the cumulative throughput amount that that particular user achieved, the player achieved. On the right-hand side, clearly, almost all of them improved, as you can see. We also added 2 evolutionary algorithms, one genetic algorithm and another one called recursive random search, just to make sure that our human beings can beat them. Okay. And we did observe that. Most of the time they did. Just quick observations. On average, users were able to increase the total throughput by about 16% after the training. And the p-test value, the p-value for this experiment was significantly low enough that we were comfortable about it. And we had the failure cases, which is case number 7. Again, in this one, we did see improvement, again, all across the board, essentially, most of it, again. And the human beings did much better in comparison to the evolutionary algorithms. That's another interesting thing over there. But the amount of total increase was smaller. So that's the case. That's when we started asking why actually this is happening. And that's when actually we consulted with the psychology department and asked why is it that, with the failures we didn't see significant improvements. So then Ramona said, well, but probably you should include the fact that, you don't let the players progress before they master a particular skill. And the p-value was a little bit high, actually, in this one. You probably needed more volunteers, forced volunteers. When we did the mastery, we focused on 2 skills. Again, high bandwidth selection. Given a network, there's no failures, there's nothing. It's just that their current link weights are just set wrong in that you can just quickly find a better path for most of the flows. And the other one was decoupling of the flows that I showed earlier. So we had 7 training levels, 7 scenarios. And of course, now they have to master every level before proceeding to the other one. In this one, we were able to convince only 5 of the participants to take the experiments. I guess we just needed a better GUI, somebody fighting or something. And each experiment, the total, it took about 2 or 3 hours per user. Clearly much longer process this time because they had to master the skill before proceeding to the next one. And the setup of the experiment was again like this. There was a tutorial, there was a before training experiments 8, and then 8 was changed a little bit. It became 8 prime after the training. And again, we had 7 cases, 7 training levels, each one of them with an increased amount of difficulty, with more nodes, more links, and more dynamism. And quickly showing every single user did show some significant amount of improvement in terms of the throughput performance of the network. And the p-test was, p-value was much lower actually, and we were really confident about this one. So clearly showing that, if you do force a particular mastery level, you can teach skills, at least for those 2 skills in this particular problem that we studied. To summarize, with the first user experiment where we didn't have any mastery requirement, we saw about 16% improvement on average. And in the second one, it varied from 13 to 21, and on average, roughly a similar amount of improvement among the 5 users in the second case. It was good to see that people can outperform the heuristics, which we were expecting. Clearly, I think targeting skills and designing specific scenarios clearly give better results. So I think the art here, and we do need feedback from you, is what would be the set of skills that a network manager, network admin should have over time. Can we come up with canonical examples, scenarios, that we can use those scenarios in such an environment to train the network admins? There are so many things that can be done to further this. Of course, the quantity and the quality of the test cases, and maybe with a better GUI, needs to be there. We can focus on, rather than just throughput, we can focus on delay and loss and make it maybe more relevant to ISP practice in that sense, and add maybe what-if scenarios. give the player the capability of trying out what-if scenarios, which is, to my understanding, is a very common practice in network operation as well. And try out multiple link failures, multiple node failures. We didn't get there yet. Of course, extend to the large-scale networks, as I alluded earlier, that involves quite a bit of things, actually. Visualizing the network is a big challenge. And maybe coming up with a game environment where there are more realistic knobs which exist in the real network operation environment, rather than just red or green button being up and down. Of course, try other problems. I would love to learn, actually, about other problems that you may feel would be applicable to this kind of training. And I would love to learn more about that, please. And of course, in the long term, extend the concept to multi-ISP games. Do maybe more peering wars, make it more economic stuff, right? How would you design a game environment with that kind of multi-ISP setting? Maybe a simplified version could be played on smartphones. I've heard actually similar games exist, but more like snakes, not overlapping with each other. It's very similar. You have multiple snakes, and you want to get them away from each other. And of course, better visualization, as I mentioned earlier. Thank you.
Any questions or comments? And also keep thinking when we go through some of these research topics, what are some avenues, what are some things you'd like to see for future research? So when you come up with comments, that's always an interesting question to think about. Okay, thank you. Our next speaker is going to be Julie Percival. And Julie is going to talk about something that I think is very interesting. We're going to pause for just a brief minute here while I do something really quickly. Greg, can you bring up, there's a new version that I just saved. So can you bring up the new version that I just saved? So Julie, come on up when you get a chance, because what's going to happen is Julie has a lot of notes on her talk, so we're going to, because of the difficulty in syncing here, what we're going to do is you're going to advance the slides with this,
Okay.
and then you're also going to look at your notes over here. Instead of using your iPad, you get to use mine.
Okay, great. That'll work. So
And as soon as
here?
the slides come up, you should be able to advance them.
Okay, so, how do I go backwards?
Backwards is the, yeah.
Okay.
Perfect.
Sorry, I have a tendency for everything to fall out of my mind when I'm speaking. I just graduated from UTD. I'm a public policy and political economy student there. People from my particular program are trained in some advanced statistical methods of analysis. And, is that good? Back closer? Is that good? Okay. Sorry. So I'm from Dallas and went to the University of Texas at Dallas. I've been a long-time denizen. I'm married to an OBSD geek. And in my particular discipline, we pick a couple areas of public policy to study. And so it was natural to me to pick science and technology. So I'm here today to talk about how I believe public policy can inform some fundamental concerns about IP address management and allocation. Now, there aren't a lot of public policy researchers interested in IT infrastructure as yet, but as our society becomes increasingly connected to this kind of technology, the demand for rigorous empirical research on the management of this can only increase. Oh, there we go. Okay. So I realize that I'm not somebody who's up to the heavy technical explanations, but I'm fairly well versed in resource management. So the PhD program that I just graduated from involved learning key concepts that drive the management of many different kinds of resources used by many people under a wide variety of conditions. Well, while certain resources may look very different, they can actually be very similar, like our ducky friends here. I'm going to try my best to avoid using a lot of technical jargon, so I just want to apologize in advance if it seems very general or simple. So, I've broken down discussion to 5 parts: who this affects, some new terms and concepts, the core dilemmas, possible avenues for resolution of these dilemmas, and some ways to test these concepts. Oh, sorry. Sorry, it's not synced up, so. So, who are the concerned parties? On one side, you have people who design the new internet protocol, and on the other side, you have people who make things function on a day-to-day basis. While IPv6 was created to address the core dilemma of not having enough IP addresses, as well as some other problems, the people who needed to convert from IPv4 have been slower to adopt the new protocol than the architects and cheerleaders have expected. Now, there are some practical reasons behind this, but there are also some fundamental problems at play that implementers have had difficulty communicating to the designers. Now, my intent during this talk is to introduce some ideas and concepts from the study of resource management in the social sciences that I believe will help foster a more productive dialogue. So here's some terms and concepts, and I'm going to take a brief detour from talking about IP addresses and introduce these concepts from my discipline. So the study of resource management tells us there are essentially 4 kinds of goods: private, common pool, toll, and public. Now, keep in mind this is more of a spectrum than an absolute, and most goods fall into somewhere between these categories. It helps to imagine this more of an XY axis. So, with the X and the Y's, of course, being defined by how rivalrous or exclusive they are. So what I mean by an exclusive good is it is a thing that has a clear enforceable boundary. These are things that are tangible goods, consumer packaged goods like chocolate bars. When you buy a chocolate bar, if you don't have the money, you can be prevented from having it. A non-exclusive good is something that's generally easily available, or it's very difficult to prevent somebody from accessing that good. A rivalrous good, on the other hand, is something that's limited or restricted in some way. Once you eat the chocolate bar or consume the water, like from the examples here, they can't be reused, or they're depleted from the larger resource in some way. A non-rivalrous good is something that can be used again and again. I'd like to go a little further into types of non-exclusive resources. Common pool resource refers to a natural or man-made resource system that's sufficiently large to make it costly but not impossible to exclude potential beneficiaries from obtaining benefits from its use. Now, common pool resource situations are distinct from public goods, but they're often confused because it's difficult or costly to prevent people physically from taking things from the system without contributing to it, also known as the free rider problem. There are joint effects of individual actions. CPRs have the added aspect of scarcity. Once a person uses it, it prevents someone else from using it. A public resource is something that's extremely durable and includes projects that are intended to be used, by multiple people. So, what kind of good is an IP address? Is it exclusive or non-exclusive? Is it rivalrous or is it non-rivalrous? Now, I spend a lot of time arguing with people in social science about whether an IP address is an exclusive or non-exclusive good. Now, to my perspective, and to some of the people that I talk to about this, it's much closer to being a non-exclusive good than an exclusive good. When someone buys a computer device in a geographic area that has internet access, you get an IP address. Because it's a precondition for internet access, it's very, very difficult to prevent any one individual from utilizing the IP addresses. Now, whether it's a rivalrous or non-rivalrous depends on what point you view it from, whether you're an end user or whether you're someone who is using it as part of your business. So, IP addresses are at heart, I feel, a common pool resource that is managed by a self-governed group interested in their proper maintenance. Now, the question of whether IP addresses are rivalrous or non-rivalrous is probably at the center of why IPv6 adoption has been reluctant and slow in some cases. Now, my working hypothesis is that people who run the internet experience IP addresses as rivalrous goods, while the architects view IP6 addresses as a non-rivalrous good. I'll go into this more in just a minute. So here are some of the fundamental problems associated with public resource and CPR goods. For time purposes, I'm just going to focus on CPR good problems. The public resource problem, however, is free riders. Not that kind of free rider. Public resources encounter one major problem. These are people who take advantage of the good without contributing towards its upkeep. Now, architects are concerned with distributing IP addresses fairly and making sure everyone contributes to their upkeep, which, in a sense, is trying to deal with the free rider problem. Common pool resource problems are a little more complex, although they do struggle with the same kind of free rider issues. It takes a different form because the resource is more limited. Individuals will use the resource at different rates. Rules that can seem fair to people who just use a little bit of the resource aren't fair to individuals who use more of the resource. Depletion of the good is almost inevitable according to traditional public policy beliefs. However, why do we think that depletion is inevitable? So this is a game theory strategic model. Imagine two individuals acting with complete knowledge of what the other is doing. The rational action is to only use the resource when it's needed, right? However, the rational response for another actor's non-use of the resource is to use the resource. This results in what game theorists call the tragedy of the commons. It's a variant of a strategic game that's also known as the prisoner's dilemma. Now, popular belief in social science was that an outside actor was needed to intervene in situations where CPR goods existed. However, Elinor Ostrom demonstrated that the tragedy of the commons game was excessively simplified and didn't reflect successful self-governed arrangements. So both public and private interventions for managing the commons have benefits and drawbacks, as I explain out here. Elinor Ostrom argued that these solutions were overly simplified, so she proposed another. The public problems essentially boil down to an inefficient use of the resource and slow response rate to the individuals who are actually using the resource. The firm has a tendency to be overly aggressive and deplete the resource quickly. However, in the case of self-governed control of the commons, Ostrom demonstrates that there's a solution available. Individuals can and do act in their best interests by cooperating together to best utilize their common good. I'd just like to note that for her work in this, she was awarded a Nobel Prize in economics and is the first woman to have done this. So, how do we resolve IP allocation and management dilemmas? Ostrom identifies 8 qualities that are present in healthy, strong, self-governed organizations. Now, looking through this list, it was clear to me that IT infrastructure governance organizations are in good shape. In fact, they actively try to do many of these things. So, what's the problem then? Why has IPv6 adoption been so difficult? My working hypothesis is that some underlying problems in IP address maintenance and allocation were unresolved by the introduction of IPv6. While the problem of not having enough addresses was successfully resolved, there are no mechanisms in place to encourage users to optimize their IP address blocks. IPv4 users are going to continue to hoard these addresses, even if it's ultimately not in their best interest. So before I finish, I'd like to just go over what I think the main points are that I think people should take away from this. Now, while the real estate analogy is a useful one to describe IP addresses to people who are unfamiliar with the concept, IP addresses are more like fresh water and how we should be managing them. However, you don't need to take my word for it. That's what research is for. Oops, sorry. So, one of the ways to test my hypothesis for IP address efficiency is just simply to look at the size of how routing tables have changed over time, controlling for numbers of actors. Now, I know this kind of data exists, and I'm working on getting access to it. How it will work for IPv6, ICANN or AARON could test the effects of different distribution rules using standard experimental protocol, by creating a test group or control group composed of similar actors, but giving the second one different rules. Another method to test this wouldn't necessarily need to be live. Agency-based modeling is currently used in social science to examine similar kinds of behavior with biological and ecological systems. I think I ran through pretty quickly. I want to say thanks, and if you guys have any questions, feel free to ask.
So I actually have a question. I think Jeff might have a question, but go ahead, Jeff. Why don't you get started?
Jeff Houston, A. Penick. Oh, that's sensitive. I think the issue about whether IP addresses themselves are a common pool resource, a private resource, etc., are less interesting than the actual issue of how did this industry get itself to a place that nobody ever thought it would, where we're now operating the internet largely on V4 without any more V4 resources. You know, we've driven ourselves not to the edge of the cliff, we've just skated right off it. Now, if you think about that transition as a market, not the addresses themselves, but the transition, I think the real question is that market showing market failure? Were the players unable to understand the signals of the resources they were consuming? And if that market was truly a market failure in economic terms, what traditional market failure resolution mechanisms should we be applying to this problem?
Well, I think that what Aaron's doing right now and trying to get a lot of you interested in getting feedback from you about your problems with IPv6 adoption, I think it's part of the process, and I think having honest and clear feedback about what the problems are can help with that. Now, at least that's what Ostrom would indicate.
I'm not sure that the participants in any of the regional internet registry communities accurately reflect the true diversity and economic value of the internet itself and the pressures that are being brought to bear on the addressing system. And placing the agenda on the RIRs to get out of this mess is kind of asking for divine intervention where none exists, which is why I was kind of hinting at this issue that we've driven deep into public policy land without the tools and techniques and analysis to get ourselves out of this.
That's why I think this is really important to do research on, because if you can model systems like this and model the effects, that I think we can actually come to a little better understanding of how people act with given certain conditions and rules. I mean, set aside a block of IP addresses and set up some rules and see how people respond to that. That's totally possible.
Well,
thank you for your question.
Sorry, Julie Yeagley. I have a little bit of a comment on that, because I think at this point, any experiment that's conducted with IPv4 addresses is probably occurring in the corner of a room that's on fire. And so if there happens to be a window in that corner, I can pretty much guarantee that everyone's headed for it. So, I mean, I think one of the important takeaways from this is that the researchers in the late 70s who came up with this were not economists, and they also weren't planning for this to be a public good at some point in the future. So self-restraint was not an early property of this system.
Yeah, I think IP addresses are pretty unevenly allocated. I mean, if you got in early.
Yeah, I'm not sure fairness necessarily was the biggest problem. It's actually it does have a lot of properties to do with when you arrived. But I think that particular fishery is probably damaged beyond repair at this point.
Well, if you could give some of those people who are sitting on those IPv4 addresses and not using them some incentive to trade them off.
Yeah, I'm sure that we will have an opportunity to find out what the highest economic purpose of some of those addresses is, because even the ones that are tradable will be enough to do that. It's just that even if they were all market commodities, there's still not enough of them.
Yeah.
Right, because we can't actually slice them into fractions, which we can do with fish or other sources of protein, for example, or water. So if we get to conduct interesting experiments with this, they're probably with the V6 address space. And people don't think of that as being a scarce resource. But that's kind of depends on how you use the bits. And people don't use the bits the same way they do in V4, which means they can blow through it at enormous rates with relatively little impact on the global routing table. I think one of the places to look at this from a research vantage point is at that address space, because even with the relatively limited usage that we have relative to V4 address space, like funny things are going on up there, right? You could ask me why it is that when I go to an RIR in one region, I'm allocated V6 prefixes based on the number of V4 prefixes that I'm allocated. In another region, I'm an LIR, and in another region, I'm allocated based on the number of POPs that I have.
It would
right?
be
Those are very interesting policy experiments that are actually going on right now among the RIRs with V6, and I think they have really funny effects.
Microphones are closed after this question. Next question.
As you were talking, you were relating.
And name and affiliation.
Sorry, Bill Nash with VMware. As you were talking, you're relating the allocation of IP address space to water. Is there a space to look at what other industries are actually doing with the exact same problem? I mean, if you take California's water usage issues into context, where you have industry resisting changes to the way they do things when they have a massive water resource, right off their coast that they could be retooling to actually use. Mm-hmm. Do you see a connection between what that industry is doing and what our industry is doing, where we have a massive resource we're not using because we just don't want to change it?
I think that there are definitely some lessons to be learned from other groups like this, from other self-governed organizations who manage resources like this for this community. And, I'm not really in any place where I could suggest anything at this point about, what would be a good way to manage the resource. But, I was hoping just to bring some of the ideas and concepts to you guys so that you could think about these things and think of how, well, if this is true, what does this mean for us? What does this mean for, how can this tell us how to do things better? And, I find it very frustrating in my particular discipline that presenting this to a social science audience is completely flipped, because I have to spend a lot of time on the technical details and, justify, oh yeah, this is an exclusive or non-exclusive, and, but
It seems to me that in terms of like a policy debate versus a technology debate, we can take this exact argument that we're having with IPv4 address allocation and look at the historical water rights distributions arguments that we've been seeing for centuries now. Yes.
That's why you see NANOG, yeah.
Yeah. Thank you.
So
Thank you for your question.
very briefly, and this is really just a comment, but when I look at all the comments, it sort of sounds like, especially when you look at Jeff's characterization of where we are now with IPv4, it sounds like the answer, the outcome, the equilibrium of some sort of game theoretic model. And is it a prisoner's dilemma type model? Is it something else? Do we understand the model that we went through in IPv4 and where we are and how we got there? And can we model IPv6 the same way and figure out where we are on that model and where we're going and how we need to change the incentives?
Exactly.
I think that's a really interesting avenue for further research. We obviously need more people versed in things like game theory, rational choice theory, public goods theory, involved in the IP address distribution. So Julie, I think you have at least a need. I don't know if there's demand for your services, but certainly a need for the stuff you're doing.
Thank you.
Okay, our next speaker or speakers is going to be Mike Smithassen, and I don't know, Brian, if you want to come up, and Brian's shaking his head. So Mike Smithassen, in a presentation that he co-authored with Brian Tierney, will be talking about, it's going to be talking about buffers on long, fat links, basically, what we think of as high bandwidth, high latency links. And this is really an interesting thing, because in this organization here in NANOG, we talk a lot about buffer bloat and the very problematic effects that buffer bloat has. What Mike's going to talk about is sort of the flip side, which is what happens when your buffers are too low and you have very high capacity links. We seem to be having maybe some slight issues. Oh, I know why we're having issues. It's not, yeah, it's a slide buffer problem. I know exactly why it is. The display there is not mirrored, so when you put PDFs up, this is the first PDF of the day. So, Mike, thanks a lot. Sorry. Appreciate that. But anyway, just to sort of frame this a little bit, it really is an interesting problem, because the issue with TCP, if you're going to use TCP to transfer lots of data, then you have to have the proper buffers for the proper set of links you've got. They can't be too big and they can't be too small. So Mike has done some work on trying to figure out what are the optimal buffers and what are the methods we can try to determine that. Thanks. Go ahead.
Thank you.
You should be able to use your answer.
All right, so like Michael said, my name is Mike Smithassen. I'm a network engineer for Lawrence Berkeley National Laboratory, and this is some work I've been doing with Brian Tierney of the Energy Sciences Network. Quick introduction to Lawrence Berkeley National Laboratory, if you're not familiar with it. We are a U.S. Department of Energy laboratory. We're multidisciplinary, so we do research from particle accelerator detector research to nanoscale fabrication, genomic sequencing, supercomputer operations. We operate on the Energy Sciences Network. That's our primary provider. ESNet connects all the national laboratories throughout the U.S., as well as the recent extension into Europe. Lots of labs are connected at 100 gig today. There are still some that are connected at 10 gig, 1 gig, but generally the larger labs are all connected at 100 gig. So a quick note about the kinds of traffic that we're interested in. So we generally look at smallish numbers of large flows over long distances. scientists pulling data off of a particle accelerator detector or out of a scanning electron microscope or genomic sequencers and sending it to a supercomputing facility across the US. Like I mentioned, a lot of labs have 100 gig links today, and it's going to 100 gig core, so relatively high speed access links compared to your core links. We're generally looking at dedicated, what we call data transfer nodes. They're servers that are purpose-built for data transfer. That's really all they do. Right now, they generally have 10 gig NICs in them. In the future, we're looking at 40 gig NICs, kind of depending on the use case. The applications that we're primarily concerned with are Grid FTP, Globus Online, and Parallel FTP, basically just ways to facilitate the data transfers for the scientists. And kind of a use case we're looking at is the Large Hadron Collider at CERN in Switzerland. They pull about a petabyte per second off of their detectors, filter them through custom silicon, and then send it to their local data center, their tier 0 data center, which they then distribute to the tier 1 data centers across the world. And we've got 2 of those on ESNet, one at Brookhaven and Fermilab. So they were doing about 50 gigabits per second, and they're saying now with their latest changes, they're looking at 180 gigabits per second. So, a quick note on buffer blow, and I think Dave is here, and hopefully I don't do too much of a disservice by kind of giving my high-level overview of it, but the premise is big buffers result in higher latency, which ends up being bad. But typically it has focused on talking about low-speed flows, less than 1 gigabit per second, and short distances, 20, 30 milliseconds, or highly multiplexed core links where you're talking about tens of thousands of flows. Whereas what we're talking about is a small number of flows, very big fat pipes, and consuming significant portions of that with small number of hosts. So we're really talking about a difference between mouse flows and elephant flows. So on the topic of elephant flows, turns out packet loss actually has a significant impact on throughput over long distances. This is a slide from ESNet with a failing line card, where the packet loss is actually due to the line card failing, not from congestion. But what they found was that even a small amount of packet loss, I think it was like 1 in 20,000, caused a significant decrease in throughput when you're talking about continental or intercontinental distances for throughput or for round trip time. So does that mean that we're saying that big buffers are good? Well, really, when we say big, we're talking about megabytes per port or per 10 gig port, not gigabytes. And we're only really addressing the very large data transfer, so terabytes and petabytes sent on a regular basis over 10 gig or faster links. And we're talking about long distances, so 50 milliseconds and up. And for us, it's really just important to write out those microbursts. And we're not saying never drop a packet ever. It's still going to be necessary to drop 1 or 2 packets every once in a while in order for TCP to fit within that available capacity. And really, we're just trying to make sure that it doesn't get stuck in that loss recovery mode all the time. So that gets to the topic of this presentation. So how can we really tell what's sufficient? Since we're in the R&E sector, we like things that are free and open source. So we want to find some tools that were going to be readily available, open source, easy to use, and free, so that other people can go out there and do these tests themselves. And this is the basic setup. So we just have 2 switches and 4 hosts, connecting 2 hosts per switch and then connecting the switches together. On the left there, we've got a sending switch that we're primarily concerned with. We're going to swap that out for different models of switches. These are just CentOS hosts, but you could run Fedora as well, or whatever distribution, I'm sure. And then we're using network emulation to add in a delay, 25 milliseconds on each of the hosts that are going to be testing the TCP transfer. To give you a total round trip time of 50 milliseconds. And those are just the test procedures. So adding network emulation to the 2 hosts, starting up the iPerf3 server, starting up this UDP background traffic in order to cause congestion on that link without having it back off on its own. And then finally, we're starting up the TCP transfer where we're actually going to measure the throughput on it. And that's the parameters there. Just start up 2 parallel streams, run it for 30 seconds, and discard the first 5 seconds of it so we're not affected by that initial TCP startup time. And if you're not familiar with the iPerf3 results, this is pretty much what it looks like. So it breaks it down 1 second intervals per stream, the amount transferred, the bandwidth, the number of retransmits in the congestion window during that interval. And then it'll give you a summary at the end and tell you, how much was actually transferred, the bandwidth from the sender and receiver perspective, and the number of retransmits. So what we're looking at in this graph is really just the summary there for the total throughput over that 30-second test. We swapped out that sending switch for different models, different configurations. So we've got a Brocade MLXE that has tunable buffers. You can set the amount of buffers by megabytes. And so we started off at 1 megabyte, ran through the tests, saw pretty poor performance. Threw in an Arista 7150, their top of rack switch. It's got about 9 megabytes, and tested with that. Went up to Cisco 6704, which is their older 4x10 gig line card. It's got about 16 megabytes. And then we came back to the Brocade. Like I said, it's tunable, so we cranked it up to 64 megabytes. And I'll get more into that in a second, but cranked it up to 64 megabytes and kind of saw that throughput plateau there. After that, it wasn't really beneficial. And then we got a Cisco 6716, and it comes in 2 flavors or 2 options. You can set it to either oversubscription mode or performance mode, and depending on the mode, will change the amount of buffers it actually has available to you. And then finally, an Arista 7504, which comes with virtual output queuing, so it's kind of hard to tell exactly how much buffers it has, but right out of the box without any tuning, it just performed fine, at least with these tests. So this is back to the Brocade. So like I mentioned, you can tune it. You can set the amount of buffers that you're using. And we just threw some values there, 1 megabyte, 10 megabytes, 20, 32, 40, 64, 128, 256. And right around 64 megabytes ended up being where it would plateau, and we didn't see any benefit of going higher than that, at least on a 10 gig port and at 50 millisecond round trip time. So that's great. That's testing with emulation and in a lab environment, but we wanted to really see how does this perform in the real world. So a colleague of mine at Brookhaven National Laboratory in New York was kind enough to lend me a couple of his test hosts that I could do transfers to and actually measure the throughput for. So the test is actually not that different. We're just throwing ESNet in the middle there and doing our transfers over it. We've still got a 2 gigabit per second UDP background traffic to force that congestion on that link, and then we're doing a TCP flow and measuring its throughput. So this is a comparison of real world versus simulated round trip time. And actually, Dave pointed out just before this that there's actually a limitation on network emulation by default. So I need to go back and rerun these tests. I think it probably won't change the overall concept, but it might account for some of these differences that we see between the emulation and the real world round trip times. Oh, and something I should mention about this. So this is testing with Juniper EX4300 and an MX80, because the MX80 will actually let you tune your buffers as well, although it does it by percentage rather than just saying I want 20 megabytes of buffers. We suspect that it probably has about 384 megabytes of buffers, which would put 20% at about 76. I actually ran some other tests in the simulated environment, incrementing it by 1% from 14 to 19%, and it ended up kind of plateauing around 16 to 17%, which would correspond to 61 to 65 megabyte buffers at those values, which is consistent with what we saw in our previous tests. So that's great. iPerf3 will let you do simulations for data transfers, but we wanted to see if we could detect buffers in a different way, or small buffers in a different way. So if you're getting packet loss, perhaps the cause of that is due to insufficient buffering. So we've got a similar test setup as before, except for we threw a third switch in between, so we could see, does it make a difference if there's congestion at different hops? And then we moved the host that sends the 2 gigabit per second background traffic to different hops and saw, how does that affect the performance? That's the test setup. So similarly, setting up the 25 millisecond delay on the host, 2 gigabit per second background flow, and then using NUT TCP and varying the burst size to actually see how that affects packet loss. And we varied the rate as well, but it ended up not actually making any difference. I'll show here. So these are averages, as well as the dash line is specifically 300 megabits per second. But from 100 to 600 megabit per second, it looked exactly the same. It's really the burst size, the number of packets that ended up making a difference. So what we see at the bottom there along the x-axis is packets, a number of packets. So from 100 to 600 packets, we tested a couple of different switches, a Juniper MX80 configured to 50% buffers, which is sufficient enough for these tests. Didn't drop any packets across all of the tests. A Juniper EX4300 and Arista 7120, which is their older switch. Those had very predictable packet loss at 300 packet burst size. So that leads us to the conclusion, if you run this test with only a 65 packet burst size, you should expect to not drop any packets, whether it's a small buffered switch or a large buffered switch. But when you increase that to 300 packet burst size, you should start seeing packet loss. But that only applies to where there's buffering, right? Because if you're not causing congestion on a small buffer switch, it's not going to drop packets because it's not going to buffer. If buffering is the problem, there could be something else. I don't have the slide here, but I did test to see, it doesn't matter if you're doing less than 2 gigabits per second of your UDP background traffic, and not really. I mean, you will see the packet loss go down, but you'll still be able to tell a difference between a sufficiently buffered switch and an insufficiently buffered switch, all the way down to like 200 megabits per second. So it is possible to test with a fairly small amount of congestion to see if it is dropping packets. And then one last interesting thing, I didn't get to do a whole lot of testing with this. There's more in-depth, extensive research, I think, coming out of Fermilab with fair queuing in Linux kernel 3.1 and above. So this is just testing with Fedora 21 and doing the iPerf3 tests at 70 millisecond round trip time to New York and back on a small buffered switch. And just enabling FQ made a significant difference. So we were looking at less than 1 gigabit per second of throughput without FQ enabled. Enabling FQ got us up to 2.5 gigabits per second just with one command line, not having to purchase any more equipment or anything like that. So very promising. We're very hopeful that as FQ develops, we'll get interesting results out of that. So just to sum everything up, we use iPerf3 to simulate transfers. You could set it to 30 seconds, 60 seconds, 300 seconds, whatever, in order to see how it performs over some period of time with certain size of buffers. And then using NUT TCP to try to simulate bursty traffic, so you're not having to run long tests. You can just do a quick burst and see, if you have performance issues, maybe it's because of a buffering problem. Fair queuing is very promising. We're very hopeful of the results that come out of the research with it. Right now, we don't think it is a replacement for buffers or sufficient buffers, but it is very promising. So can we say how big of buffers these transfers need? Probably, but I think what is even more important from this is that with these tools, anybody can go out and perform these tests. They're free, they're easy to get, they're easy to use. So encourage people to certainly do that, share your results and share your experiences with others. So additional information, I kind of glossed over a lot of the background of buffer sizing. Jim Warner from UC Santa Cruz has an interesting page about the history of buffer sizing where he links to research papers and experiments that have been done over the last 20 years that goes much more in depth into what I could possibly explain myself. He also maintains a packet buffer page that has a table of different models of switches and routers and how many buffers they have, as well as going into an explanation of the architecture and whatnot. And then, of course, faster data that has information on host tuning, NIC tuning, and configurations for switches and routers. It's a great resource and highly recommend it. And then I just threw in a 6500 link for Cisco 6500 Ethernet modules because we still have them in our network, and I'm sure lots of people do as well. So it's nice to be able to figure out how many buffers they have. And that's all I've got. I don't know if anybody has any questions or.
Quick question. I believe you said, sorry, Ann Johnson, representing myself. You mentioned Reno for the TCP implementation.
Your microphone was working. I was talking to them to get this one working, that's all.
Oh, I see. All right, well, never mind. Your sign language wasn't interpreting correctly. So you mentioned Reno. Did you try any of these with any of the other TCP versions?
So actually, I think the Reno is on the test slide for the failing line card. We actually use HTCP for all of our tests. I did test Cubic as well, but in my very, very brief test, I didn't see any significant difference between HTTPC and Cubic.
Okay, so clearly your point about the tools is general. It was just if you had got around to testing a different TCP implementation, it'd be interesting. Thank you.
So I have a quick question. If you calculate the bandwidth delay product and try to take that and calculate how much buffer space you should need, does that jibe with your results? I mean, if you try to do it all on paper, does it do this? Does it give you similar results, or is it sort of counterintuitive based on that?
I think it makes sense if you're talking about small number of flows, right? And I guess it depends on what formula you're using for calculating BDP, because I know people have talked about using BDP over the square root of the number of flows. Since we are talking about very, very small numbers of flows, I think for the most part it kind of does. But again, I encourage people to go out and test that and see how it performs for them. Yes.
Dave Top, upperblood.net. Thank you.
Hi, Dave.
I did want to try to clarify one thing, and that what I call SCED-FQ scheduler in the Linux kernel is the first pure fair queuing scheduler that has ever existed, and as such, it's fascinating. But I believe that your excellent results are actually coming from another attribute of that code, not fair queuing itself,
Oh, really?
which is the packet pacing feature built also into that, which is the fallout of being able to do perfect fair queuing. So I look forward to looking harder at the pacing portion of it.
Yeah, and I know Brian has done some with pacing as well, but I didn't have a copy of his slides for that. Anything else? All right, thank you.
Thank you guys very much. And I want to just reiterate that the inability to get the slides up for Mike's talk was my fault, because that is something I should have tested prior to this. So sorry about that, Mike. The next talk, you may have noticed we're kind of moving sort of from the researchy stuff kind of into the operational stuff now. One of the things I like to do at this track is provide some of the network operators a chance to talk about some of the things they do. So I sort of call this RNE network personals or regional network personals. We're going to kind of do a combination of that and an interesting project that's happening, that's underway. John Hess of Scenic and Camille Crittenden of UC Berkeley are going to be talking about some of the things that Scenic does here in California. That is the research network for California. And they're also going to be talking about something called the Pacific Research Platform, which is an attempt to link together a set of well-connected research universities and the data transfer nodes, which they have, the Science DMZ type infrastructures, which they have. We've talked about the Science DMZ before here in the research and education track. They're going to have a quick slide on it. So John and Camille, come on up. You're the last talk of the day, so enjoy.
Well, thank you. So as Michael introduced, I'm John Hess with Scenic, and Camille Crittenden from Citrus at UC Berkeley has joined me, and together we're going to provide some context for this Pacific Research Platform. So what is Scenic? Scenic, as one was mentioned earlier in this track, is one of those 501(c) not-for-profit institutions. Scenic stands for Corporation for Education Network Initiatives in California. And the mission is to advance education and research throughout California, providing world-class network essential for innovation, collaboration, and economic growth, connecting California to the world. So Scenic was formed by 5 charter associates, the California Community Colleges, the California K-12 system, California State University system, private universities including Caltech, Stanford, University of Southern California, as well as the University of California system. So what is CNIC as a network? We have about 3,800 miles of optical fiber within California. That's a combination of dark fiber that's owned or leased with IRUs. And we have members in all 58 counties that connect to CNIC. About 10,000 sites, a lot of eyeballs, and we're governed by the members at the segment level. So as far as what we do with this infrastructure, we have kind of networks that run on top of this, one being the CalREN Digital California Network, operating as AS2152, and that's what our members use for the commodity internet access, email, web browsing, video conferencing, etc. We also run CalREN, California Research and Education Network, and that is a high-performance research operating as AS2153. And again, that is pretty much R&E only for interinstitutional collaborations. We also have a third network that we call Experimental Developmental, XD, and this is for making resources available to conduct research on the network in and of itself. So CNIC partners with the Pacific Northwest Gigapop to run what is Pacific Wave, which is a distributed exchange that extends from Seattle in the north through Sunnyvale and Los Angeles here in California. And this is operated in collaboration with University of Southern California and University of Washington. And so this provides our researchers connectivity to national networks, NRENs, such as Internet 2, international networks in connecting in North America, as well as other international networks connecting our research to collaborations throughout the world. So for the last couple of years, we have a series of initiatives. Pacific Research Platform is one of them. I just want to mention one of the other major ones that we're doing is connecting the California Public Libraries. This is a major initiative connecting about 1,100 libraries in over 100 jurisdictions throughout California. This is either increasing their connectivity, lowering their costs, or both. So Camille is going to introduce the science driver aspects of the Pacific Research Platform, so I'll turn it over to you.
Great. Good afternoon, everyone. Thank you, John, and everyone for sharing the platform this afternoon with me. I thought I would give you just a few bites of what we're going to do with this high-performance network under the grant that we had proposed to the NSF that will ultimately build out the Pacific Research Platform. It's really a collaboration between two multi-campus research institutes. CITRIS stands for the Center for IT Research in the Interest of Society, which is based at UC Berkeley and encompasses some of the Northern California campuses, including Davis, Santa Cruz, and Merced, and working together with Larry Smar down at UC San Diego, who is the director of Cal IT2, and that is between San Diego and Irvine. So between the two of us, we cover 6 of the 10 UC campuses, and together we're charged with creating new IT solutions for society's most pressing problems. So it's viewed through that lens of social benefit. We have a number of research initiatives that there's some crossover between the two multi-campus research institutes in health, in the environment, in robotics and connected communities, and nanotechnology. So we're really going to be drawing on some of the faculty members that we work with most closely to be some of the science drivers and science driving applications of this enhanced network. So through the Pacific Research Platform, there's a quick abstract. It's building on some previous grant-making programs through the NSF that some of the individual PIs at the different campuses have received. So the idea behind this is to really draw on that collective expertise and bring people together to learn best lessons from each other. And these are the 5 areas, the science drivers, that we're really going to be focusing on. In particle physics, also working with some folks from the Lawrence Berkeley Lab, as you heard from before, in astronomy and astrophysics, in biomedical applications, so a lot of the genomic research and microbiome type research where there are PIs on multiple campuses. In the earth sciences, looking at geology and the Pacific earthquake engineering research that's happening at a number of the different campuses. And then also on virtual reality and visualization applications. A lot of that's happening at Irvine, UC Irvine, and elsewhere. So we'll be excited to see how that new infrastructure can help to really advance some of those scientific applications. There's a little bit more detail about some of the specific projects in the astronomy side, really trying to connect the instruments that are being used to collect these vast amounts of data and to make sure that it's coming right into the researchers and faculty members' offices and labs as quickly as possible. And the earth sciences will include some of the climate modeling, and then also the virtual reality applications, as I mentioned.
So Michael had mentioned that there's the model of the Science DMZ, which has been presented here before. So this was one slide from an earlier presentation of the Science DMZ, a larger talk that was presented earlier. So 3 critical components, and there are kind of 4 bullets here, and we'll touch on that. So the idea here is that the architecture of the DMZ creates a friction-free network path for the science data to move off the campus into the wide area network to the other institutions that the researchers need to collaborate with. We also talked in the previous presentation of these data transfer nodes that are high-performance hosts that are purpose-built for wide area network transfers. So all the host tuning that needs to occur, as well as the tool sets that are available on them, are optimized for these transfers and also their ease of use by researchers. And then another critical element is the instrumentation of the Science DMZ. I believe Brian Tierney is giving a session tomorrow on Personar, so highly recommend attending that. And then in this case, the 4th bullet is the engagement with the end users. This is bringing together the science researchers themselves with the networking folks, understanding the workflows that are involved in the science and mapping how the networking can enable that science to occur, either moving larger data sets more quickly or in a way that doesn't involve putting hard drives on FedEx and shipping them across distances. So again, more details at fasterdataes.net. And this is very similar content, just organized in a different way to the previous slide. Again, I would say this slide highlights the engagement process because that's what really can drive the success of that effort. So as we've talked about, we're very grateful for the National Science Foundation in funding various elements of our research at the various campuses. The CCIE, CCNIE programs have funded Science DMZ implementations at over 100 US campuses. So this is a large impact to R&E across the US. So the challenge within California is that a number of our UC and other R&E institutions have either received funding for implementing Science DMZs on their campuses, and the challenge that we have is interconnecting them in a more seamless fashion. And so that's what brings about the idea of the specific research platform. So we talked about a little bit about Pacific Wave earlier, that we would use Pacific Wave as a backplane for this data-intensive science. There are a lot of pieces to the data movement problems that are otherwise unavailable to scientists. And the task that we're trying to achieve with the Pacific Research Platform, again, is integrating the science DMZs across the West Coast. So we see this as something that is extensible, regionally as well as nationally. And the goal is to get the sciences that the data they need, where they need it, when they need it. So what we set about beginning in last December is to develop a proof of concept that can this be done? Can we do this on a regional scale? So, and then work with the scientists to map their research to that Pacific Research Platform. So we developed a version 0 as an experiment involving many of the UC campuses, a number of the private institutions in California, as well as with ESNet and NASA Ames and University of Washington. And so what we did, we concentrated on the regional aspects of the problem, and we mostly focused at the intercampus piece. So over a 10-week period, lots of folks at HPC staff and network engineers collaborated to build a mesh of the perf-sonar nodes and implement a measurement and debugging dashboard. Again, this is a MAD-Dash. This is a software that was developed as part with ESNet, by ESNet and others, and deploying data transfer nodes to sites who had not yet developed their own, as well as using grid FTP as part of the Globus server package to conduct file transfers to quantify throughput. We built a partial BGP ring mesh across the fabric of Pacific Wave to demonstrate the potential of networks with burst capacity greater than that of a single DTN. And along the way, we identified some specific optimizations that were needed. We've found and in some cases fixed a few problems in pursuit of gathering the data. And then we also identified some anomalies for further investigation. So this is in this case, what a perf-sonar MAD-Dash can look like. This is a full mesh where each of the nodes tests to all the other nodes. In this case, this is kind of like an eye chart. These nodes are organized by latitude, beginning at the top on the left-hand side from a node in Washington to the south, going to a node that's located at San Diego State University. And here there are thresholds that are set for green, corresponding to capacity rates that are measured above 5 gigabits per second, and yellow for indicating somewhere between 5 and 1 gigabits per second. And you may notice on this graph or this chart that there are kind of groupings. And so that, as you might expect, groupings of nodes that have lower round trip times are going to tend to have clusters of green. And that one of the things that we found is that network problems that manifest over distance may not manifest locally. So we talked a little bit about the DTNs. One example of which is a device that was developed at UCSD is another NSF grant, which is referred to as a Fiona for a flash IO network, flash IO node appliance. And this is here the driver was to develop as a high performance node at low cost. So I'll refer this for more information on generic DTNs. I'll refer you to one of the faster data es.net links off their Science DMZ page. So again, as I mentioned, we used Globus Connect server suite for their grid FTP tools to effect transfers among the DTNs. In this case, it was reference data, and we used cron to schedule the transfers to occur over periods of time. We also used an ESNet contributed script that parses the grid FTP logs and then load those transfer results into an Esmond measurement archive, and then which allowed the MAD-Dash dashboard to reach into the archive and visualize the results, similar to how the perf-sonar results are visualized. So I guess one thing I'm not showing as a slide is that behind this grid are time series graphs that, similar to what we've seen earlier today, that can measure forward and reverse throughput, latency, loss, and in some cases, an archive of traceroute information between nodes. So what are our next steps and near-term goals? So we developed this proof of concept. Now we need to migrate it into something that's more persistent. As part of that, one of the initiatives that we have within CNIC and Calren is a 100 gig layer 3 upgrade to take our Calren HPR network from a 2 by 10 gig north-south network to a 100 gig network north-south. We want to expand the perf sonar deployment that not only CNIC has, but also encourage perf sonar deployments at our campuses beyond which they already have. So we're also received funding from the UC Office of the President for stabilizing and expanding the deployment of data transfer nodes among UC campuses in addition to what is existing. And we also are looking toward to incorporate federated authentication among those DTNs for shared access to those resources. And we're beginning the process now of engaging with the scientists at the various institutions to begin to map their research to the Pacific Research Platform. And then again, one of the challenges that are faced at the individual campuses are last mile issues, bringing the researchers, labs, and connections to have access to the data transfer nodes at the science DMZs. Long-term goals? Well, we're looking to try to create an integrated West Coast Science DMZ, where, again, to quote another ES, that person where geography is irrelevant to our researchers. And that, again, that we are basing our model on ESNet's Science DMZ model. And so we're advocating other regional RNEs to follow ESNet's example. And that the idea being of promoting DMZ interoperability across regions, nationally and internationally. And throw up a bullet for SDN and SDX, just because it seemed like a presentation wouldn't be complete without an SDN and SDX bullet. But moving for commercial services, one of the questions that we have not yet answered fully is how will commercial services play in our model? Right now, most of our efforts are focused on shops that have RNE shops that develop their own compute and storage resources, but there's if you will, a spot market for compute and storage that Amazon AWS and Microsoft Azure or Google have an answer to that already a number of our researchers are making use of. How that plays longer term as this develops is something that we have not yet answered. So this is just another graphic representing the collaborative effort among multiple institutions within the region. And that is showing about 20, I think there are about 20 institutions involved in the current model of the Pacific Research Platform. So again, some links. This is another slide from an ESNet presentation. So please, these are great resources. Make use of them. And we'd be happy to take any questions you may have. Thank you.
If nobody else has questions, I have one. So just for contrast with one of the earlier talks, so Dave Temkin from Netflix was describing the infrastructure that they're building. Do you have any feeling for how the volume of data that you're shipping around compares to the volume of data that Netflix is moving over the internet?
I guess that's a good question. I have an answer.
I asked that very same question, actually, and I can't express it in quantifiable terms, but Larry Smarr, because there was a lot of information or news about Netflix and the percentage of people all watching House of Cards at the same time or whatnot. And his indication was that the size of the data is even as large as it is, it's much, much smaller than the size of the data sets and data that's being moved for these science applications. So I apologize that this isn't my technical field, but I appreciate the question. And that was the general answer that I had gotten.
Joel Yeagley, CDNs typically break very large objects up into smaller objects. So I would be extremely surprised if you saw object sizes bigger than, say, 50 megs or so, right? The whole data set may be much bigger than that for a movie, right? If it's 4K, it might be, several tens of gigabytes for one movie, but the individual components of that are being moved around are much smaller.
Thank you.
Yeah, I think, again, this was, as the previous presentation, we start talking about the mouse flows and elephant flows. And so the research data is typically going to be fewer large flows of the elephant flows.
So just a brief comment from me. Do you think about Dave Temkin's talk too? There's a lot of similarities in what, say, a Fiona box is trying to do, maybe different scale and maybe different, some differences, but there are some similarities between what a Fiona box is trying to do and what the Open Connect stack is trying to do that Dave was talking about. And so a lot of things he was talking about kind of reminded me of sort of science DMZ, GTN type things. It's not that different, I think, although there are at least some similarities in terms of what we're doing. And also when you look at other commercial drivers, like, for example, athletic conferences transferring high-def game videos and things like that, which they're doing a lot of now. The studios are actually transferring movies within the studios to different production facilities, and they're using the network to do that, and they're transferring things like 4K videos and stuff like that. I mean, do you think there's interesting overlap with a lot of what the commercial folks are doing now, especially when you consider that we're using compute power within Amazon and some of these other organizations? It was like a Merv Griffin question. It was a long question. The answer was yes.
So, Joel Yeagley again. The biggest flows I saw in a previous life with a commercial application were actually things like mem-based backups. So, assume you have several thousand databases, shards, sitting someplace, and you're backing them up across the country, and you're doing that kind of continuously. So that might be 40 gigabits per second for like 50 flows between two data centers on different sides of the country. So there's a lot of applications that actually look like that because they're doing replication real time, and they're relatively large flows, but they're not consumer, right? So they're between two, much like yours, they're between two endpoints that we know about already, and we can manage those because they're special and weird and not sort of part of our general purpose traffic shaping or anything.
And Joel, just when you were aware of these kinds of applications, were they sort of enclaved in a way that resembled kind of a science DMZ, where they're not going through this sort of standard front door corporate firewall type stuff?
Sure, yeah. I mean, you might have these big ASIC-based firewalls, but they typically have capacity on an individual flow basis that is limited by the size of the ASIC. So, for example, we had stuff into S3 when I was at Zynga, which is 2 years ago now, that was 40 gigabits per second, 24 by 7, 365. That was, the network was engineered specifically for that flow, up to and including the recipient of it, which was, a company we were paying money to.
Okay, well, we've got a few minutes to walk over to, we're actually late, sorry. Okay, thanks very much for coming. I appreciate all of our speakers. We had a really nice collection of talks this time around, really nice diversity and interesting set of topics to go through. So thank you very much to all of our speakers. If you do want to run over to the peering personals, that is over, I believe it's in California, which is where the newcomers lunch was. That's upstairs, go over to the center stairs and then go up, and then just follow the signs. There's also nice interactive maps there. Thanks a lot, folks. Otherwise, see you at the social. Drive safely.